So welcome. Uh, we are now going to start using all the concepts that we talked about regarding mass transfer, the microscopic balance, the mass transfer coefficient, and so on in some problems. So let's get started. Just to help you revise, this is what we have done. This is where we are. We are going to talk about parts 8 and 9 together. We are not going to talk them separately. Uh, the concepts that we talked about in the last lecture, just a quick revision of that. If you answer these questions, it will automatically revise all these concepts. What is meant by thermal and concentration boundary layer? Right? Expressions for Fick's and Fourier's law. What is the physical significance of the dimensionless numbers Peclet number, Prandtl number, Schmidt number? A fluid with low Prandtl number will give higher or lower rate of heat transfer? That's the question. Make your pick. A fluid with high Schmidt number will give higher or lower rate of mass transfer. Again, take your pick. Okay. So this will help you to revise. Now let's go forward. These are the equations that we might want to use if you are using microscopic balances: Cartesian coordinate system, cylindrical coordinate system, spherical coordinate systems. This is from Appendix B 11 of the Burt Stewart Lightfoot's book, Transport Phenomena. And they have written it in terms of WA, the mass fraction, but we have written it in terms of concentration. Concentration and mass fractions you can relate one to the other. Don't worry too much about the why that mass fraction and the velocity that they talk about, velocity of the mixture they talk about. So don't worry about all these things right now. These things will get clear as we go along. Okay, this is what we want to do, either microscopic balance or macroscopic balance. Okay, just a reminder from the previous class, we have to pick either this or this path or this path, okay, and go accordingly. Okay, to remind you about this macroscopic balances, mass transfer flux is going to be proportional to concentration driving force, and the proportionality constant we are going to say mass transfer coefficient. Okay. So Na, the flux, we are going to say is K, mass transfer coefficient multiplied by delta C. Sometimes this K we write in little differently. We write this K, if you want to write it for liquid phase, we write it as KL. If we want to write it for gas phase, we write it as Kg, because sometimes both mass transfer might be there in both the gas phase as well as the liquid phase. So just to know which phase we are talking about mass transfer, we write it as K subscript L or K subscript G. Okay, so depending on which phase we are writing, you can even think of this as flux is equal to concentration driving force divided by sorry, let me just correct that mistake. Okay, that is corrected now. We can think about flux as driving force divided by resistance, and then this 1 by K we can write it as resistance. So that was the error that I have corrected. So mass transfer resistance is 1 by K. So mass transfer coefficient, mass transfer resistance, they are just inverse of each other. Higher the mass transfer coefficient, lower is the mass transfer resistance. Think about this as an analogy, electrical analogy if you like. Current is equal to voltage driving force divided by the resistance. Okay, and this resistance concept is going to become important when we start talking about mass transfer between different phases. You could have a resistance in one phase, you could have a resistance in another phase, which means mass transfer coefficient for one phase, mass transfer coefficient for another phase, and then you can compare relative magnitude of those resistance and see which one is important. The one which has a lower resistance, you can neglect that mass transfer resistance, right? And then you can just write in terms of the main resistance. So that's the importance of writing it in terms of resistances. We are going to use it again in our next coming semesters. And mass transfer coefficient depends on geometry, just like friction factor depends on geometry, okay, for momentum transfer. Higher the agitation, higher is the mass transfer coefficient. So to obtain this mass transfer coefficient, we are either going to use empirical equations, theories of mass transfer, analogies of momentum, heat, and mass transfer. We'll see all these as we go along. Okay, here is a problem. Imagine that there is a spherical medicine tablet like this dissolving in water. Okay, assume that the water is very large, infinite if you like, as compared to the soil, as compared to the medicine tablet. So assume that initially the tablet has a diameter of 5 millimeters, so diameter is 5 millimeters. It has a density of 1200 kg per meter cube. Assume that the tablet is purely made from solid drug A, that is a molecular weight of 400. Usually the tablets contain, along with the drug fillers and maybe sugar and so on, to make it more sweet so that people can take it. Right now, for the purpose of the problem, let's just say that it is pure A. Assume that the solubility of the drug in water is 0.1 kilomoles per meter cube. Okay, solubility in water is 0.1 kilomoles per meter cube. For simplicity, assume that the tablet is suspended in water and water is stagnant and quantity of water is very large. What does it mean? That even if all the tablet dissolves, the concentration of A in the water is going to be very, very small, negligible. That's the meaning, infinite amount of water. Okay. How much time? I want you to answer. How much time would be required for 90% of the drug from the tablet to dissolve in water? Assume that diffusivity for A in water is 10 raised to minus 9 meter square per second. Let me just correct that. Yeah, so I just corrected that subscript. It should be proper. Diffusivity of A in water, molecular diffusivity, is 10 raised to minus 9 meter square per second. So here is a small picture to visualize. So think about how you're going to do this problem, what strategy you are going to adopt from here. Okay, just because it's the first problem that we are solving, let me give some more clarity. So in the immediate vicinity of the tablet, that is the interface of the tablet and the water, we are going to say that concentration of A in water is always in equilibrium between the solid and the liquid. So the concentration in the immediate vicinity is equal to the solubility. That means concentration in the immediate vicinity, it is by thermodynamic equilibrium. So the concentration here is the solubility just in the vicinity of that solid tablet, because the interface is always saturated. Interface is always at an thermodynamic equilibrium. Just like when we say water has a vapor pressure and the bulk concentration can be lower, partial pressure can be less than the interface concentration, vapor pressure, just at the bulb of the thermometer. Remember what we said? The bulb of the thermometer, wet bulb thermometer, just in the immediate vicinity of this wet bulb, it is in equilibrium, it is having a vapor pressure, and in the surrounding air it is having a partial pressure which is less than the vapor pressure. That is, vapor pressure is the thermodynamic equilibrium between the liquid water and the water in the vapor state. Same way, now the thermodynamic equilibrium is between the solid A in the solid form and A in the dissolved form. You will do more about equilibrium in the next in the class on thermodynamics, but we are going to say now that let's call this as Ca star. What I want you to do is draw first a profile of how Ca in water, how concentration of A in water varies with distance. So profile means how it would vary with distance. Okay. Draw that for yourself. Okay, because it's the first problem, I'm just drawing it for you. So if you think about this as an infinite medium, water, there is a tablet here. This is 5 millimeters. So if you take r equal to 0, it's a spherical tablet, so radial coordinate we can take away from the tablet. So if r is equal to 0 is the center of the tablet, so this is the radius of the tablet, or dp by 2, this dotted line. So just in the immediate vicinity, concentration is Ca star, and away from the tablet in the radial direction, Ca tends to 0. Ca goes to 0 in the bulk, okay, far away from the tablet. This concentration profile. So if you are able to visualize this concentration and you are convinced about this concentration, then go forward. Otherwise, pause and think and do it for yourself. Okay, think about what strategy we want to adopt. Microscopic or macroscopic, accordingly solve. Okay, let's go back. Microscopic or macroscopic? Microscopic, if you think, is the flow laminar or no flow situation? Yes, water is stagnant, so I might as well do this. I don't need to do this. This I don't need to consider. This I don't need to consider. Flow is not turbulent. Flow, no flow situation, stagnant, so this is straight away applicable. If microscopic is applicable, and we can solve this. Why should we go for macroscopic? We should not go for macroscopic. If microscopic, that's our first priority. If I can do microscopic, it always is better, because I can get more information rather than straight away doing macroscopic. So microscopic is the first priority, right? I'm going to need this again and again, so I'm going to delete all these markings, but we are going to do microscopic now. Okay, so take control volume as the tablet. Okay. This drug is dissolving, so this tablet is going to shrink as more and more drug dissolves. So diameter of this tablet is going to reduce. Okay, so if we take this as a control volume, tablet is as a control volume, then we can write accumulation is rate of mass coming in minus going out. Mass coming into the tablet is 0, obviously. Mass going out of the tablet is what is the rate of mass transfer. It is what is the dissolution of the tablet. Okay, so and accumulation, we can write mass of the A in the tablet at any time t minus mass in the tablet at any time t plus delta. Now just remember that mass, I am saying mass, but we are writing automatically in terms of moles, because the solubility, all those things I have given in terms of moles per liter, kilomoles per meter cube, right? So rather than saying mass, we might as well, or we should really be saying moles at any point of time, because we are going to write mass transfer in terms of moles. Let me also, just for the sake of correctness, let me just correct that as well. Okay, here is what we have written now, corrected. We are writing in terms of moles. Moles at time t minus moles at time t plus delta t. Moles at time t, volume of the tablet multiplied by density, that will give you mass of the tablet, mass of A in the tablet, because tablet is purely A, divided by molecular weight. This will give you moles of A in the solid tablet at any point of time, minus moles of A in the tablet at any time t plus delta t. So this accumulation must be equal to what comes in minus what goes out. What comes into the tablet, obviously 0. What goes out of the tablet is mass transfer rate. Dissolution, mass is getting transferred, A is getting transferred from the tablet, dissolved near the interface, near the surface interface, and away into the bulk of A. That is where mass is getting transferred. A is getting transferred. Mass transfer rate, how would we write? K A delta C. And K, if you write mass transfer rate, it is kilomoles per second. K A meter square, delta C kilomoles per meter cube, driving force. So K, mass transfer coefficient, has units of meters per second. Kilomoles will cancel out, meter square, meter cube, you will get meter in the denominator. That will give you meter per second when it goes to the other side in the numerator, meters per second. Okay. Now if water is stagnant, can we use microscopic balance? Yes, to get the value of mass transfer coefficient. This situation, which equation would we write? It's a spherical tablet, so we better take spherical coordinate system. Where is that? Yeah, that's here. So use this equation. In this equation, can we simplify? Only this term is going to remain, right? Concentration does not vary with theta, concentration does not vary with z, there is no velocity, stagnant, these are 0, this is 0, reaction is not there, all this is 0, only this term is going to remain. Right now I have dropped this term as well, because it is what we call as pseudo steady state. Let me just explain. Okay, so our equation would be like this. Our equation would be like this: del Ca by del T plus V dot del Ca del dm del square Ca, and velocity is 0, stagnant, so this just drops out. Del Ca by del T, right now we are saying is quasi steady state. That means concentration variation with respect to time, the mass, the molecular motion is so fast. Molecular motion is so fast, the time scale for change of tablet size is so large. The molecular motion is so fast. That's what is the meaning of quasi steady state. So that will give you If you write for delta square using appendix of Bird-Stuart-Lightfoot, you will have dm 1 by r d by dr of r square dCA by dr. It's a second order differential equation in Ca and R. For Ca in R, boundary conditions at r is equal to dp by 2, that is at the surface of this tablet. R is equal to dp by 2 is describing the surface of this tablet. Ca is Ca star. At r tending to infinity, far away from the tablet, Ca is tending to 0. Ca is 0. Okay. Diffusivity will cancel out. R just cancels out. So you will get r square dCA by dr is equal to some constant A. A is a constant of integration. Go from here to here. Integrate once, take r square on the other side. Integrate once, you will get Ca is equal to minus A by r plus B. B is another constant of integration. Now these constants of integration A and B, we have to evaluate using the two boundary conditions. So if I use boundary condition 2, as r tends to infinity, Ca tends to 0, this implies that B has to be 0. So Ca would be minus A by r. If you use the first boundary condition, at r is equal to dp by 2, Ca is Ca star, we will get the value of A, right? And then concentration of A we can write as Ca star dp by 2r. And if you plot this profile, if you plot Ca by Ca star versus r, you will get this profile. It's like a it's a 1 by r dependence. You will get this kind of dependence. Plot this and see for yourself. Okay, why are we doing this? We have to get K, mass transfer coefficient, so that we can put it here. Okay, let's do that. What is the flux of A from the tablet? It is Na is minus dm dCA by dr evaluated at r equal to dp by 2. dCA by dr, what do we have dCA by dr? dCA by dr is A by r square, right? And A value we already have. A is minus Ca star into dp by 2. So dCA by dr, if you substitute, you will get this. This is to be evaluated at dp by 2. So you will get Na as dm Ca star dp by 2 4 by dp square. If you rearrange, Na is equal to dm Ca star 2 by dp. Let me just write this little differently. Here is some things that we need to talk a little bit more about. Okay, this Ca star is actually a driving force. It is actually Ca star minus 0. Concentration difference, concentration driving force. What is the concentration driving force? Ca star to 0. That is the concentration driving force. Right? So what I have written? I have written flux is equal to concentration difference multiplied by all these other terms that are there. So this is the flux, right? Concentration difference, driving force, it is actually Ca star minus 0. But minus 0, whether I write or I don't write, it's the same. It is the driving force. So mass transfer coefficient would now be 2 molecular diffusivity divided by the particle size dp, diameter. So K would be 2 dm by dp. Now look at this. I can rearrange this expression. K dp by dm is like a dimensionless mass transfer coefficient. Just like we say friction factor is a dimensionless momentum transfer coefficient. Tau w divided by half rho v square. Just check K is in meters per second. Look at the previous slides. K is in meters per second. dp is in meters. Molecular diffusivity is in meter square per second. Right? K dp by dm is a dimensionless mass transfer coefficient. We are going to call this dimensionless mass transfer coefficient by a special number, by a special name, or in honor of person who used it for the first time. We are going to call this as Sherwood number. Sherwood was a person who worked in the area of mass transfer. It is going to be denoted as SH, Sherwood number. So Sherwood number is 2 in this case. So Sherwood number for mass transfer from a sphere in an infinite medium is equal to 2. So whether the sphere is of 5 millimeter, 4 millimeter, 3 millimeter, 1 millimeter or 20 meters, that is the advantage of using dimensionless numbers. We can apply it to any sphere of any size, diffusing, or substance from that sphere diffusing in an infinite medium, any medium, because it accounts for dp, it accounts for molecular diffusivity. Now, right, we had this expression. All I have to do is now put this. So minus d by dt, pi by 6 dp cube rho s by molecular weight. I've just divided throughout by delta t, taken the limit as delta t tending to 0. Do that for yourself. Make sure you get it. Must be equal to the rate of dissolution or nothing but rate of mass transfer. Rate of dissolution. Dissolution is happening because of mass transfer. Right? Is minus d by dt. This term is equal to Na flux evaluated at r equal to dp by 2 into area, which is the same as k into area. Flux is the same as k into the driving force Ca star minus 0, and k is nothing but Sherwood number equal to 2. This gives you the flux equal to 2 molecular diffusivity Ca star by dp. So minus d by dt, let me rub this, otherwise it just gets cluttered. Right. Okay, so minus d by dt, just simplify now, it's straightforward. Ca star pi dp square, area of across which mass transfer is happening, area perpendicular to the direction of mass transfer. Mass transfer is happening in the radial direction, area perpendicular to the radial direction, area perpendicular to radial direction is the surface area of the sphere, pi dp square. Okay, simplify. You will get this expression. Integrate with respect to time. Now it's the first order differential equation in time. Integrate that. Initial condition you will need, we call it as initial condition. T equal to 0, dp is initial diameter. So you will get this expression, dpi square minus dp square is equal to 8 molecular diffusivity Ca star molecular weight into time by rho s. This you should get on your own automatically now, from based on whatever I have told you about. Once you get this, let's go forward. Okay, if you don't get this, go back and see where you have not got. Okay. Once you get this, go forward. Okay, so here is the look at the right side first, don't look at the left side. Okay, dpi square minus dp square is equal to this same expression as previous. I can divide throughout by dpi square, you will get 1 minus dp square by dpi square. I have divided by dpi square. Now if I take mass, I want 90% to be dissolved, right? So I want to talk in terms of mass, so I have to relate the particle diameter to mass. How do I do that? dp cube into pi by 6 into rho s divided by molecular weight tells me the moles. So m by mi, mass at any time divided by mass initial, is dp by dpi cube. So dp by dpi square, which is what I have here, is m by mi raised to 2 by 3. So I can substitute that now here. 1 minus m by mi raised to 2 by 3 is this bracket into t. Now again, writing, advantage of writing in the dimensionless form. Left hand side is dimensionless. It's a ratio of mass at any time t divided by mass initial minus 1 minus that number. T by tau. So time, if I write tau would be rho s dpi square 8 dm Ca star molecular weight, just reciprocal of this. It's a dimensionless time, T by tau. So tau is the time scale for dissolution, meaning it is how much time is required for complete dissolution of the particle. Okay. So if you want 90% dissolution, m by mi is 0.1. So if you substitute, T by tau will be 0.785. Again, advantage of writing dimensionless form is I can write this expression, I can use this expression for any other tablet, for any other diffusivity, for any other solubility Ca star, for whatever I want dissolution, 90%, 50%, 70%, same I don't have to drive everything again. That's the advantage of writing in dimensionless forms. You will find that tau is 26 hours and time required is 0.785 times 26 hours, means roughly how much? 20 to 23 hours. 26 into 0.8 roughly, if you see, it's about 20 to 23 hours. Okay, make sure you get this answer. Here is something I want you to think about. Imagine that this was inside a patient. Patient has taken a tablet to get a cure, to get rid of his symptoms. This time required is very large, 22 hours, 23 hours. Patient will go without relief from symptoms for several hours. Now, that's not a good idea. So drug delivery is a very important subject. Question I am proposing to you is, how do you reduce this time? Look at this equation. That's the advantage of writing in the dimensionless form. I can reduce the time required for dissolution if I reduce tau. How do I reduce tau? Several ways. dp if I reduce, dm if I increase. Molecular weight, of course, we don't have a choice. That's a drug molecule. It's a property of the drug. Right? dp I can reduce, dm I can increase, cs star I can increase. Okay, think about all possible solutions. Just to tell you a little bit about pseudo steady state. Okay, time scale for change of particle size is 26 hours. In 26 hours, the 90% of the particle is dissolving. That's the time scale. Meaning, if I divide by this time scale, t by tau is a dimensionless time, t bar if you like. And t bar is going to go from 0 to 1. That is the meaning of time scale. Time scale for dissolution, time scale for change of particle size. Whereas time scale for concentration, diffusion, is by molecular motion. Molecular motion is of the order of several meters per second, 4-5 millimeters in size. So molecular motion sets up the gradient dCA by dr very quickly. That's why we have neglected this del CA by del T and treated it as if it's a steady state diffusion. But steady state at every instant of time, as if steady state is reached, because we are integrating with respect to time. At every instant, a steady state is reached because it's a molecular motion. So time scale for molecular motion is very fast. Time scale for change of particle size is very gradual. That's why we call this as quasi steady state or pseudo steady state. This allowed us to simplify this. Okay, think about that. Here is what I want you to think about. What are the possible drug delivery options? First of all, let us think. If I want to take a tablet for relieving a symptom, so I want concentration of drug in the body, in the blood if you like, as a function of time. T equal to 0 is the time where I take the tablet. What do you think is a curve that patients will prefer? How do you think this profile looks like? Patients, what kind of profile would patients prefer? T is equal to 0 is here. That's where we are taking the tablet. This is where we are taking the tablet. What profile would patients prefer? That's the question that I'm asking. Okay, draw. This is what patients would prefer. As soon as you take a tablet, concentration of the drug in the body reaches a good level and remains at this good level forever. So the patient doesn't have to take any other tablet. And this is the concentration at which the medicine takes effect. You don't want it to be higher, side effects will happen. You don't want it to be lower. The relief from the symptoms will be that much less. What happens in reality? What happens in reality? As soon as you take a tablet, let's say at T equal to 0, you're taking a tablet, but all it takes time to dissolve. not 26 hours, but it takes time to dissolve. If I adjust the particle size and so on and so forth, it takes time to dissolve. Now all of it dissolves. After some time, it reaches a very high concentration. All the side effects of the drug start. You feel giddiness, nausea, all those things. And now the body, is a drug is a foreign substance, body is able to uh, throw it out of the kidney or whatever mechanism, digest it or throw it out of the body. The concentration falls with respect to time. So patient feels relief, or patient the drug concentration is above the minimum value required only in this period of time. That is the window in which patient feels relief. So what do doctors tell? Oh, don't take just one tablet, take another tablet after 6 hours or 8 hours. Second tablet, third tablet. Remember, the green thing is what patient would like. Take one tablet, instantaneous relief forever. The whole drug delivery ball game is how do I match this green profile, this blue profile. This is where it is effective. All the drug is lost here, wasted. This drug, which is concentration over and above, that's too much drug. Side effects come. Okay. So what are the possible options? Make a tablet of varying particle size. Take a tablet which is a mixture of small particles and large particles, and as soon as you take that tablet, it disintegrates. The small particles dissolve quickly. Small particles dissolve quickly. Let me take another color. Small particles dissolve quickly. I get a very high concentration. Okay, and the large particles now dissolve slowly. Okay. That's one option. Or take a tablet, coat it with some polymer. Coat it with some polymer. Polymer dissolves, some drug comes out initially very quickly, and then you have now the drug diffusing through this polymer coating. Slowly it diffuses. It doesn't allow it to reach a peak. You maintain it at this concentration for a long time, and then you take a second tablet somewhere here. Oh, sorry. Take a second tablet here. Polymer coated tablets. They are very common. Very common. You see description of some medicines that may be there in your house. Many of them would be polymer coated. Or think about a different mechanism. Let's say don't have an oral drug, have a drug as a patch on the skin, and then the drug will slowly diffuse through that skin. Slowly diffuse. It's a patch that you apply, and then the drug slowly diffuses from that patch through the skin. It is taken up into the body. Then you can reach this green profile. Obviously, drug will vanish or get over after some time. You just replace by another patch. Okay. So drug delivery is essentially a mass transfer problem, and chemical engineers are the most ideally suited for drug delivery because they understand mass transfer. They can quantify, they can calculate. Okay. Doctors will tell you what drug, doctors will tell you what concentration, but chemical engineers design drug delivery systems. Let's go forward. Okay, another way of increasing increasing the dissolution rate and reducing the dissolution time is if I can increase the mass transfer coefficient, because the rate is proportional to mass transfer coefficient multiplied by the concentration driving. So if I can increase mass transfer coefficient, how do I increase mass transfer coefficient? Agitate. Okay, here's the next problem. So water containing the tablet is now vigorously stirred to keep the tablet suspended in water. So there is always a relative velocity of the water with respect to tablet equal to its terminal settling velocity. Now, how much time would be required for 90% of the drug to of the tablet? So what I'm trying to say is now, so imagine that water is there, tablet is there, the drug is water is stirred, so the drug tablet also gets stirred, but because it is heavier than the water, the drug tablet relative velocity of the drug tablet with respect to water is equal to the terminal settling velocity, slip velocity, relative velocity. Okay, solve this problem. Okay, pause the video, solve it for yourself. Only when you have solved, go forward. What approach would you like to take? Microscopic, macroscopic? To help you decide, here is some mechanistic picture. Okay. So there is a water tablet stirrer which is going to stir. So if you look at the region near the tablet, here is what you see. This is the tablet. Of course, you are looking at a small region, so curvature is neglected as if this is one tablet. Okay. There is a boundary layer here, and flow is here, agitated liquid is there. So there is a bulk of water and there is a boundary layer. What does the boundary layer consist of? Again, microscopic picture, still microscopic. There is a tablet here. Within this boundary layer, there is a laminar sublayer, viscous sublayer, there is a buffer layer, there is a turbulent core, and concentration is going to reduce like this within the boundary layer. So now if it is vigorously stirred, obviously we have turbulent flow. What do I do? Is the flow laminar? No flow situation? No, that's not the case. Is the flow turbulent? Yes. Do I have turbulent diffusivity? Do I want numerical solution? Well, I can, but it will take time to numerical solve a partial differential equation. Right? Let's go with now macroscopic balance. So we are not going to even do this. We are not going to use the turbulent microscopic balance. We are going to use a macroscopic balance. Okay, let me rub this because we are going to come back to this again in the next problem. Okay, here we are. Okay, now can you solve with this macroscopic approach now that we have chosen? Let me solve this problem also for you so that you are comfortable. So due to vigorous agitation, flow will be turbulent. Therefore, if we use microscopic balance, we need to numerically solve. So we will go with a macroscopic balance. Again, accumulation is rate of mass coming in minus rate of mass going out. What is our control volume? Tablet. Rate of mass coming into the tablet? 0. Rate of mass going out of the tablet is mass transfer rate. And if I consider an interval of time delta t, mass transfer rate multiplied by delta t is same as earlier, accumulation. Instead of mass, we should be writing moles. So this minus Ka delta C minus Ka Ca star minus 0. Water is still infinite. Bulk concentration is still 0. This is still 0. Okay, minus Ka Ca star. Now, how do I get values of mass transfer question? Again the same question. Empirical equation, theories of mass transfer, analogy of momentum, heat and mass transfer. Let's do some quick calculation. Okay, remember it is going to be dependent on Reynolds number. Okay, so I need to know Reynolds number. For Reynolds number, I need to know relative velocity. Relative velocity is decided by terminal settling velocity. If it is decided by terminal settling velocity, as particle size changes, terminal settling velocity also is going to change. Let's just for our simplicity, our understanding, calculate the terminal settling velocity for different situations. Let's say initial. Let's say, oh, where is that go? Yeah. Yeah. Oh. Okay, here we were. Okay. So in the last problem, we had Sherwood number equal to 2. So K dP by dm was 2. Sherwood number was 2. K would be 2 into 1 into 10 raised to minus 9 divided by 5 into 10 raised to minus 3, about 4 into 10 raised to minus 7. Now due to vigorous agitation, K will be higher. Okay. Let's assume right now that K is 1 into 10 raised to minus 5 for now and solve the problem. do that, minus d by dt pi by 6 rho s dp cube molecular weight k pi dp square c star. I hope everybody is now clear about this. If not, go back and make sure that you have understood this first step. Simplify. K, now I am going to tell you, I have straight away told you the mass transfer coefficient is 10 raised to minus 5 meter per second. It is much larger than this. Vigorous agitation. This was when it was stagnant. Now it is vigorously agitated. I am just going to give you a value right now. Integrate. Again, as before, you will get this expression. As before, dp by dpi is cube is m by mi. So dp by dpi, that's what we have now, is m by mi raised to 1 by 3. So 1 minus m by mi raised to 1 by 3 is now this t by tau. Tau is now this rho s dpi 2k ca star molecular weight. For 90% dissolution, m by mi is 0.1. Put that here. T will become 0.536 tau. So tau, if you substitute, rho s 1200, 5 into 10 raised to minus 3, that's dpi. 2 is there, k is there, c star 0.1, molecular weight 400. Tau will be 7500 seconds, or t will be 1.12 hours. By having mass transfer coefficient, which is now, let's say, 100 times more, not 100 times actually, it is about 4, so about 25 times more. 25 times more. Okay. Our time scale has reduced by a factor of 25. 26 hours has become 7,500, about 2 hours. Right? That's how agitation helps. And fortunately, in our stomach and all that, motion is there that generates turbulence enough to increase the mass transfer rate, so that our patient feels relief very quickly within a 1 hour. So that's why people advertise relief in 5 minutes, 6 minutes. On what basis do they calculate? They calculate based on this. Okay, now I'm going to give you now next problem, same problem as before. Relative velocity now is the terminal velocity. And empirical equation that relates Sherwood number is like this. Sherwood number is equal to 2 plus 0.6, Reynolds number is to 0.55, Schmidt number is to 0.33. This is for turbulent flow around a sphere. It is not applicable for anywhere else. It is applicable for turbulent flow around a sphere. People have done this by experiments and proposed this relationship. Okay. Sherwood number is, we have defined it earlier. Reynolds number we have defined earlier. Schmidt number we have defined earlier. Now, as particle size is changing, terminal velocity will change. Okay. Let's look at this in a little bit more detail. So to calculate mass transfer coefficient, we need Sherwood number. For that, we need Reynolds number. For that, we need terminal settling velocity. To calculate terminal settling velocity, what do we need? Archimedes number. And Archimedes number will change on dp. It will be initially value will be something else, finally value will be something else. So if I look at Archimedes number based on dpi, it is 2.45 into 10 raised to 5. That's highly turbulent. So CD is 0.44, right? So this means CD is 0.44. And terminal velocity can be written as 1.75 multiplied by square root of dp delta rho g by rho f. It's not Cp, it is CD. 0.44. You see how momentum transfer is helping us to solve a mass transfer problem. How momentum transfer is helping us to solve mass transfer problem. That's why momentum transfer I wanted you to be thorough. Oh, I have already written CD is 0.44. Right? Let's look at some values. At the start of the process, terminal velocity, if you calculate from this formula, is 0.17 meter per second. Reynolds number for the particle is 850. Sherwood number is 173. You can see that Sherwood number is far larger than 2. Even at the end of the process, Vt is 0.12. Archimedes number is still large. Reynolds number for the particle is 278. Sherwood number is 99. It is far larger than 2. Why I am comparing with 2? Because 2 was the Sherwood number for mass transfer from a sphere in an infinite medium, stagnant medium, no turbulence. Now because of the relative velocity, there is turbulence. So Sherwood number is going to tell us how much is the mass transfer as compared to a stagnant condition. Higher the Sherwood number, higher is the mass transfer rate. Okay, so go forward. Same as earlier, minus dy dt pi by 6 dp cube rho s by molecular weight is k a Ca star. It is Ca star minus 0. There is no water is infinite. That's why the bulk concentration is 0. Put Sherwood number. Sherwood number is equal to 0.6, REP raised to 0.5, Schmidt number is to 0.33. So it is actually 2 plus, but that 2 is very small, so I can simplify it. I don't have to worry about this 2 at all, because the next term 0.6 REP raised to 0.5, 0.33, Schmidt number is to 0.33. That is very large as compared to 2. I can even neglect that 2. If I neglect, it will become 170. If I neglect, it will become 171. If I neglect, it will become 97 as against 99, right? So whether I include that 2 or I don't include that 2, it's not going to make much difference. So I neglect that to make my life simple. Now I can substitute. So in this expression, what do we know? Pi by 6 we know, 3 we know, rho s we know, molecular weight we know, dm we know, 0.6 we know, rho fluid we know, Vt is going to come from here. It is going to be again related to particle diameter, right? Vt is going to be a function of particle diameter. Mu f we know, molecular diffusivity know, rho f we know, pi we know, 4 we know, Ca star we know. So I have one differential equation in dp. It is just that this differential equation is complicated. It is not nice. It's straightforward. It's a first order differential equation, but the dependence on dp is not so nice, right? As before, solve and get a time required for complete conversion, and now you see whether it is 1.2 hours or 24 hours or whatever. Okay, see for yourself, calculate for yourself. I am not solved this ahead. I am not solved this forward. It is up to you. Okay. Once you are clear, let's go to the next problem. Okay. Only once you are clear, so go to the next problem. Okay, here's the next problem. We want to make sugar syrup for making some food product. Let's say you want to make a cake or a biscuit or something that requires, say, Indian sweet, something that requires sugar syrup. Okay. You have to make 10 kgs of sugar. You have to dissolve in 20 liters of water. Assume that all sugar particles are spherical with an initial size of 1 millimeter. Hardly unlikely, but not realistic, but yeah, okay. Assume that it's a sphere with an initial size of 1 millimeter. Density of sugar particles is 1.5 grams per cc. Solubility of sugar in water is 4 gram moles per liter. Assume that due to constant stirring, the value of liquid side mass transfer coefficient is independent of particle size, and its value is KL equal to 5 into 10 raised to minus 6 meters per second. Normally, Sherwood number depends on particle size. Mass transfer coefficient depends on particle size. Just to make your life simple, I have just given you some constant value of KL. Assume that diffusivity of dissolved sugar in water is 1 into 10 raised to minus 9 meters square per second. Now estimate the time required for 99% of the sugar to dissolve in water. One hint for you. As the sugar dissolves, now this time water is not infinite. Water is finite. 10 kgs is to be dissolved in 20 liters of water. So concentration of dissolved sugar in the bulk of solution is not 0. It is finite. That's a hint. Okay, solve this problem for yourself. Pause the video, solve it for yourself. Here's the solution. Okay, so when 99% sugar dissolves in water, 10 liters, our concentration of sugar is 10. where is that? 10 kgs of sugar, 99% of that in 20 liters of water. So it should be 20 liters of water. It should be 20. Well, let's make that correction. Yeah, okay. 99% sugar dissolves in 20 liter of water. So mass of sugar dissolved form is 0.495 kg per liter, 1.447 kilomoles per meter cube. Now this is large as compared to CS. This is large, it is not 0. So driving force now is 4 minus 1.447 if everything is dissolved. And as more and more sugar dissolves, this concentration of sugar in the liquid, in the solution, increases. So if you think about it, what we had earlier, we had Ca star going to 0. Now that's not going to happen. This, because liquid is finite, initially it may be from Ca star to Ca equal to 0, but after some time, as sugar dissolves, this Ca goes up. So after some time it will be like this. After some time it will be like this. After some time it will be like this. Okay. The Ca is going to build up with respect to time. So driving force is going to change with respect to time. Okay. Account for that. Account for that. Okay. So if you have not solved it already, now with these hints, solve it. Pause the video, solve it. Here's the solution. So if I say, let's say NP is the number of sugar particles, now that's going to remain constant. Okay, we are saying that particles don't disappear, all dissolve at the same rate, and each particle is dissolving. And let's say VL is the volume of solution, that also is constant, 20 liters. Right? 20 liters. Okay, so as before, minus d by dt, number of particles now, pi by 6 dp cube rho s by molecular weight. This is for one particle. Multiply by number of particles. That's the total solid, balance for total solids. As if my control volume is all the solids put together. KL into A into delta C. So KL into NP into pi by 4 d square. Surface area of all the particles. Now KL I am writing is the liquid side of mass transfer coefficient. Ca star minus Ca bulk. Ca bulk is not 0. It is not constant. Ca bulk is concentration of dissolved sugar in water. Ca bulk increases with time as more sugar dissolves. So to get Ca bulk, we need to write balance on sugar remaining in the solid form and that in the dissolved form. Do that. Pause the video. Go forward from this point. Okay, here is the solution. What is the initial sugar, initial moles of sugar? Np into pi by 6 dpi cube rho s divided by molecular weight. That's the initial moles of sugar in the solid form. This, at any time, these moles, either they are in the solid form as undissolved or they are in the liquid form as dissolved. So that is, in the solid form, it is at diameter is dp at any instant of time. So this is moles of sugar initially. They must be equal to moles of sugar in the solid form or moles of sugar in the liquid form. What is in the liquid form? Ca, concentration of sugar in the liquid multiplied by volume of liquid. So Ca, if I can rearrange from this expression, would be this initial moles minus moles at any time in the solid phase divided by VL. This numerator is how much sugar is dissolved from the solid phase at any instant of time. Okay. So now our balance, this expression, we can write this right hand side like this. Now you solve analytically or numerically. Numerically you can solve on a calculator, right? Or analytically also you can solve, that's also okay. Numerically if you want to solve, you can use Excel, you can use Simpson's 1/3 rule or trapezoidal rule, or analytical you can solve. Okay. Analytical solution is possible here. Okay. Solve it. Okay. Get an answer for yourself. So next time somebody in your family is preparing a sugar syrup, you can tell them that, look, I can tell you exactly how long you need to stir and how much sugar will remain undissolved, how much sugar will dissolve at any instant of time. Okay. Provided the mass transfer coefficient you know properly, or if you know the data, you can back calculate mass transfer coefficient. Right. Whatever we have discussed so far is in two parts. It's in momentum, heat and mass transfer, Welty's book. chapter 28, sections 28.1 to 28.3, that talks about stagnant medium and so on and so forth. And chapter 30 tells you mass transfer coefficient relationships in terms of Sherwood number, Reynolds number, Schmidt number for different situations. Okay, so read these two chapters, solve problems from the back of these chapters. Each of these chapters, there are several problems that are given. Solve some of them. That's why we have kept 12 hours for this part. Lectures are not going to go on for 12 hours. You are going to need time to solve the problems. That's why this is there. So solve problems from the book. Get all these concepts. How we take balance, how we are writing mass transfer rates. Okay. We'll stop here. In the next class, we will solve some more problems.